All right, so over the last couple weeks, we've been talking about the atmosphere, and more recently, we've started talking about weather that is occurring in the atmosphere. So we're going to take a few formal notes on some weather phenomena, some of which we've already talked about, and then we will move on next week to start talking a little bit about climate. You should be following along with your note guide, and you should be filling out some of the definitions of important words and ideas as we go through. If you like, you can pause the lecture to fill out some information and then resume when you're ready. You can also rewind and re-listen to a part that you would like to see again. Let's get started. Weather and climate are two things that can be a little bit confusing. We talk about both of them a lot. We talk about what is the weather going to be like tomorrow, and we talk about the climate is changing and different things like this. And so it's important to know what both of those terms mean when we use them. Weather is the conditions of the atmosphere, generally the troposphere, the lowest layer of the atmosphere, over a short period of time. So when we talk about weather, we're talking about things like, is it dry? Is it hot? Is it raining? Is it cold? And things like that. Climate, on the other hand, is talking about how the atmosphere behaves regionally over a long period of time. That's how we define climate. So the climate in a place like Arizona is very different from the climate in Washington State. In Arizona, the climate is a desert. It's very dry and very hot. But in Washington State, it's very temperate. They have very low, stable temperatures, and they experience a lot of moisture and rain off of the Pacific Ocean. So those are two very different climates. So when you're talking about something like climate change, it's important to remember that individual weather occurrences, like a really cold winter or the blizzard that's happening in the East Coast right now, don't determine climate, because that's not a long period of time. It's a short period of time, like one winter or part of one winter. And so we'll be looking next week at long-term data about the climate and exploring how we analyze that as well. And the main difference between weather and climate is just time. Weather is really short-term and climate is very long-term. When we study the atmosphere, we call it meteorology. And so when we are looking at the atmosphere, we know it's a bunch of air, but we want to check out a couple other things about it as well, like what is its moisture content, how much water is in the atmosphere, and also what is the pressure of the atmosphere. Atmospheric pressure is something that we experience all the time, every day, but we never really think about. It's just the force exerted by all the air molecules that make up the atmosphere. And so every day there are millions and millions of air particles that are running into you and exerting a pressure. As we've talked about previously, the pressure at low altitude, at sea level, 0 miles or 0 kilometers here, is very high, 1,000 millibars, compared to the pressure on top of the mountain, Mount Everest, which is only about 300 millibars. And as you go higher and higher into the atmosphere, the pressure gets less and less and actually approaches 0 as you get out into the exosphere. The reason for this is that this ocean of atmosphere pressing down on us is less when you're higher in the atmosphere than if you're at sea level. So just think of this ocean of atmosphere pressing down on you, and remember that you experience less pressure when you're higher up and there's less atmosphere to press down on you. This is another good example, this water bottle, of how atmospheric pressure can actually be observed. If you were at the top of a 14er, so a really tall mountain in Colorado, like Gray's Peak or Torrey's Peak or Long's Peak or something like that, you had an empty plastic water bottle, and then you sealed it tightly and observed it on your way down the mountain. As you go down the mountain, the air pressure is going to increase. And so because the pressure outside the bottle becomes greater than the pressure inside the bottle is going to start to be crushed and collapse. And so halfway down the mountain it might look like this, and when you're all the way down the mountain, the bottle will be totally crushed. In addition to atmospheric pressure, we can also talk about atmospheric moisture. So when we're talking about moisture, we're talking about how much water is in the air. And the term we use for that is humidity. How humid is it? Humidity is a measure of the amount of water vapor in the air, which can be a useful measurement for us. But what is often more powerful, and what you commonly hear about on the weather on TV, is relative humidity, which is a ratio of the amount of water currently in the air to the maximum amount of water vapor that the air could contain at that temperature. So if you consider the figure at the right, we have water vapor at 10 degrees Celsius, and the air is holding the maximum amount of water vapor that it can possibly hold. So it's 100% relative humidity. Over here at 20 degrees Celsius, we have a yellow circle which shows us how much water the air could hold, but the blue circle is the water vapor that's actually in the air. And since the air could possibly hold more water, the relative humidity is only 52%. If we increase the temperature again to 30 degrees, we can see that the air could hold even more water, but since it's still holding the same amount of water vapor, the humidity relatively is only 28%. In all three of these cases, the actual humidity is the same, but the relative humidity is different. And that's why relative humidity is a more useful observation for us to make. Dew point is another measure of atmospheric moisture. Dew point is the temperature at which the water vapor in a sample of air condenses into a liquid at the same rate in which it evaporates. So all the time, water is condensing from the air onto surfaces and then evaporating back off of surfaces into the air. And at temperatures below the dew point, the water actually leaves the air and starts condensing on things. So if you've ever had a cold water bottle that got a layer of water condensation on the outside, that's what we're talking about. Water condensed onto a solid surface is called dew. So often in the summer, when you get up in the morning, there will be dew on your lawn from water condensing onto the grass at night when the temperatures are cooler. This graph on the right shows the relationship between humidity, temperature, and dew point. So if we look at this, when we're at 100% humidity and we're at really high temperatures, the dew point is very high. It's unlikely that the water will come out of the air and condense onto anything. But as it gets cooler, when our humidity is high and the temperature is lower, it's far more likely that the dew will occur. We have a much lower dew point. And it makes sense also because if you have less water in the air, so these are decreasing humidity with each colored line, then we're going to have a lower dew point because there's less water in the air. The final form of atmospheric moisture is precipitation. And precipitation is water that's released from the clouds as rain or freezing rain or sleet or snow or hail or something else like that. And this is what we commonly think of when we think of atmospheric moisture because it's the easiest for us to see and experience on a day-to-day basis. Next, we want to talk about how air moves in the atmosphere. So we're going to review 3 types of air movement that we've already covered, and then talk about a couple new types of air movement that we have not discussed yet in class. To begin, we'll talk about temperature inversion, which occurs when cool air and smog become trapped in a valley by a layer of warm air on top. So this happens in cities like Los Angeles and Denver because we have cool air coming off either the ocean or the Great Plains, and it mixes with the smog in the city, and then this blanket of warm air on top causes the cool air and the pollution to be trapped. So This is a really good example of what happens in Denver on a regular basis. We have that layer of warm air on top trapping the smog and pollution and the cooler air in the city. Two other types of lifting we discussed were convectional lifting and orographic lifting. In convectional lifting, there's a hot spot like a parking lot or a field or something like that, that the sun heats up and it causes the air around it to warm up, and the warm air rises, and at the same time cool air is actually sinking to the ground to be heated, and then it rises up again. And so you get this circular motion which causes cumulus clouds to form and thunderstorms to occur, which is why we have a lot of thunderstorms in the Midwest. There's a lot of flat land that serves as hotspots there. Orographic lifting happens when air is pushed up the side of an obstacle, commonly a mountain, and as it gets pushed up, all of the moisture condenses in that air mass to form clouds and precipitation. And so on one side of the obstacle, there's a lot of precipitation, and then on the other side there's something we call a rain shadow where there's no precipitation. It's a very dry region because all of the moisture left the air on the other side of the obstacle or mountain. The new types of air masses we'd like to discuss are called fronts. So a front is the contact zone between two different masses of air, and you can actually hear them talk about fronts when you're watching the weather on television. And frontal lifting occurs when these two air masses collide and one front goes over the top of another front due to a difference in pressure, temperature, and moisture content. And this causes a lot of interesting weather to occur. Specific fronts that we need to know about are cold fronts, warm fronts, and stationary fronts. In cold fronts, cold air encroaches upon the space occupied by warm air, which causes storms and precipitation. In a warm front, warm air is encroaching on cold air, which causes precipitation and storms to occur also. Stationary fronts happen when neither front is pushing the other one or going under or over it. And so they are sort of equally matched and neither front is moving. And this causes very stable weather conditions over the region where stationary fronts have settled. Last thing we're going to talk about is violent weather. Lightning is a fantastic example of violent weather. It is an electrical discharge from the clouds to the ground, and it's caused by an electrical charge being created by little water droplets rubbing against each other in the clouds. When lightning discharges from clouds to ground, we hear thunder accompanying it, which is a loud rumbling or crashing noise. And this is actually caused due to the rapid expansion of heated air. Lightning is very hot and heats up the air around it, and when that air expands rapidly, it creates a loud noise. Last two types of violent weather are tornadoes and hurricanes. Tornadoes we talked about a lot in the NOVA video, but as a formal definition, they are funnel-shaped clouds that extend down from a storm and rotate at a great speed. Hurricanes are similar to tornadoes in that they rotate, but they're actually very different because in a hurricane, it's a large tropical thunderstorm that features powerful circular winds, and so the entire storm is actually spinning as opposed to just part of the storm, like in a tornado. Hurricanes are very dangerous and often impact the southeast section of the United States, bringing high winds and lots of rain and vicious waves. So they're another very interesting weather phenomenon that occurs. So that does it for weather. We will be moving on next week to start talking about climate and studying how CO2 and temperature have changed over many years on the Earth. Then at the end of next week, we're going to look at taking our atmosphere and weather exam and moving on to our next unit. So you might want to start thinking about reviewing this unit, making sure all your work is completed and turned in so that we're ready to rock and roll when it is time to start our new unit.